and Nakata from Japan, and he'll speak about the second order reduced density matrices and applications to quantum chemistry.
Thanks for organizers for inviting me to be here. And my talk is related to second order reduced density matrix and its application. My name is Nakata Angry Bird Maho. I'm quite addicted to Angry Bird, so my middle name is Angry Bird. So here is collaborators and current and past. Fukuda-san, Brahms, Jerome Perkus, Fujisawa Katsuki-san, Yamashita Makoto-san, Michel Overton, Zenji Zhao-san, Nakata-san, Ehara-san, Nakatsuji-sensei. These are results based on collaboration with many people. So here's my Angry Bird score. I'm ranked 582 out of 36 million players. So let's play Angry Bird with me. I will beat you. So yeah, actually I'm looking for friends. seriously playing Angry Bird. So here I'd like to introduce some reduced density matrix method and the introduction of semi-definite programming. This is the key tool to solve, key tool to optimize reduced density matrix, and application to two-dimensional Harvard model. We can successfully apply this method to chemistry and as well as physics, and we state open problem arise from our researches. So currently, it looks good, but still have serious problems to solve, both theoretical and programmatical. So introduction of reduced density matrix method. So I'd like to state my problem as 98 of chemistry is explained by obtaining the ground state wave function and the total energy by solving Schrödinger equation with Born-Oppenheimer approximation with basis set expansion. So in that case, Hamiltonian can be written like that. And Schrödinger equation is the eigenvalue problem of a partial differential equation. So this is the energy, eigenvalue and energy. This is the eigenvector. Yes, okay. We have to solve this equation in anti-symmetric Hilbert space, like this. If we change the coordinate of two electrons, the minus sign appears. Schrödinger equation itself is long known, very well known, but this is a famous statement by Dirac. And here is a quote from quantum mechanics of many electron systems. The general theory of quantum mechanics is now almost complete. The whole chemistry is completely known, and my difficulty is only that exact application of these will lead to equation too complicated to be solved. So even though Dirac says so, we have huge effort have been devoted to Schrödinger equation by a chemist and a physicist. So here's our attempt. Sorry. Sorry. So let me much more clear statement for the problem what we want to solve. The core problem is determine the electronic structure of harmonic systems. In other words, determine the most stable, the lowest energy of system with n electrons. This is called ground state energy. Our quantum system we are interested in consists of protons and neutrons. Here, we consider this particle as just points, and n electrons are surrounding this neutron and protons. Then we also consider the proton and neutrons are fixed. So this approximation is famous, Born-Oppenheimer approximation. So the theoretical model of Schrödinger equation is something like minimum eigenvalue problem, Schrödinger equation, and antisymmetric. We solve this antisymmetric subspace. So antisymmetric means that particle is fermionic. This is what are interested in, chemists are interested in electrons, so that the wave function itself is antisymmetric. So the molecule has some nucleons, proton and nucleons, so that such kind of things can be treated as external potential. So the electronic equation is something like that. Z is some direct product of Cn times spin variable. The smallest eigenvalue E0 is ground state energy, and the electronic Schrödinger equation can only be solved approximately. This is unfortunate, but much more accurate solution can be done by recent wave functional approaches, but it costs very much. So we always solve approximately. So, for example, electronic Schrödinger equation has an analytic solution for one electronic system. So here is one hydrogen wave function, the hydrogen molecule, but this is exact. And Z1 should be R3 times this one. This is this indicates that the electron has a spin. So we have to solve in this space. So general scheme to solve Schrödinger equation can be described as follows. So once Schrödinger equation is known, but kinetic and potential energy of electrons should be given. So this is a external potential, so that we should optimize. We should know. Sorry. So then we obtain electronic Schrödinger equation. Okay. The next, we also approximate electronic Schrödinger equation by Born-Oppenheimer approximation, and also discrete the space of functions. So in a way, the minimum eigenvalue problem can be casted as semi-definite programming. This is the exponential size, so that we cannot solve except for a very small system or some systems which have very high symmetry. So we want to reduce the size of the problem by something compactification. Then we can also reduce. This is a convex problem, but we can also have a same convex problem with a representability problem. Then however, unfortunately or fortunately, we don't know a representability condition completely, so we need further approximations. So actually, we impose some known inequalities. Then finally, we get semi-definite programming, which is tractable size. So we know the Schrödinger equation, but we have to employ many approximations to get feasible equations. So let me explain how to discretize the infinite dimension of vector psi. Usually, wave function itself is continuous in continuous space, but computers cannot solve in a continuous space, especially for large spaces. We need very large. For example, if n particles are inside the system, then n to 3n variables are needed. So very huge number of grid points is needed to discretization. But chemists have been made a huge effort to introduce fixed basis, so that finite, even though this is a small number of set of basis that but describes the chemical system very accurately. Usually, base size R should be larger than the number of electrons. Should twice the number of electrons, sometimes much more larger, to describe the system, but definitely smaller than making some grid in the space. So we usually, smallest one used in quantum chemistry is sometimes called ST06G, and the famous one is double theta, or we know much more expensive basis functions, but the number of bases in these basis functions are all definitely finite. So what we want to do is construct n particle Hilbert space by taking antisymmetric product of the wave function of one electron. Okay, so the total whole system wave function, the whole system can be approximated by the finite number of one electron wave function, and sum over choose n from R. So there's a R basis set, and choose n basis from this, and this coefficient describes antisymmetric part, or antisymmetricity of the wave function. Then solve the Schrödinger equation. The operator appeared in the Schrödinger equation can be evaluated by one particle, one electron wave function. So then we get large size of matrix H. Usually, so in a given basis, we have a lot of approximation, but even given basis, solving this eigenvalue problem, namely Schrödinger equation, is still intractable. So, but a very small system we can solve. We can solve if the given basis and electrons numbers are very small. In that case, it is called full configuration interaction. Under this discretization, the best approximation of the ground state energy is something like eigenvalue problem, where this order is somewhat very factorial of R and combination of R and N. This is SL is space of L times L symmetric matrix. So this is a huge matrix. So we can solve except for a very small system. So general scheme here is we explain some until here. So we define the molecules and the Schrödinger equations and approximations and discretizations. Then finally, it becomes a minimal eigenvalue problem in exponential size. So this problem can be reduced to convex problem. So here is a brief description of our DM method. So this method is proposed in 1970s, reduced density matrices. preliminary computation is done in 1970s, and Garrod and Rosina and Mihalovic and Purkis, and solve accurately only in 2001 by myself and other collaborators. So, alternative. This method is alternative to the traditional electronic structure method, which necessarily involves wave function, i.e., the electronic Schrödinger equation. So what we doing is solve variational problem. This is an optimization program instead of dealing directly with an eigenvalue problem or partial density equation, partial differential equation. So our method actually first done in 1970s. What we do is systematically solved and extremely good approximation for ground state energies. It is computational good approximation. This is suspected since 1990s, but confirmed in 2001 and 2004. Unfortunately, this is not practical and cannot replace the traditional method of quantum chemistry, because we can solve only problem up to 18 electrons, maybe much more, 20 or so. But latest result of high performance computation, it can calculate 20,000 atoms. 20,000 atoms. This is not a joke. We can, if we use traditional method, we can solve 20,000 atoms.
So which kind of method?
Hartree-Fock and fragment MO method.
Sorry?
Fragment molecular orbital method or something like that.
Okay, but you would beat them on these methods. You beat on the 18 electrons.
Wait, Hartree-Fock and what else?
And density functional theory.
Density function.
And
Yeah, but density functional is not ab initio.
maybe people say so.
Yeah, they say so, but it's not.
I don't personally. I don't like density functional theory, but practically, DFT is very good. And this is trade-off between times and size and accuracy. So, if you want to calculate larger system with poor accuracy, you can calculate with Hartree-Fock or density functional theory. But if you want to calculate smaller size but accurately, you can choose our method or not so practical at this moment, but or coupled cluster theories. So here's incomplete list of 2RDM computation. The first, 1940, Fushimi first defined RDM, and FD and Meyer also defined later. And Kuhn may be the first one who find the complete and representability condition on one RDM for ensemble state. Coleman coined such kind of problem as in representability conditions, and Gerald Purkis found G conditions, and Kijewski, Garrod, Mihalovic, Rosina, Garrod, Fusco, Elder, first computations. And they somehow applied to nucleon system, but failed drastically. So that this is one reason this approach was almost forgotten. And in 1978, Elder found T1, T2 condition. This is a very complicated paper, so that digging it is quite difficult to me. And small breakthrough was done when Elder gene higher order RDM condition was defined, and some calculation is done for model system. This is our contribution to RDM theory. The systematic calculation is first done and done accurately for the first time. The potential energy surface was done by our group and also done by Mazziotti. And in 2004, this is a first implementation of T1 and T2 condition. which is very strong. And currently, if we calculate using RDM method, we always use T1 and T2 condition because it is most accurate. In this paper, we use PQG condition, which is not quite promising, but not so very accurate, which is comparable Miller-Plesset perturbation theory, but T1 and T2 are very accurate, so that almost comparable to CCS difference T, which is golden standard of very accurate calculation. And Matsuyoshi also developed the RRSDP, first order one, also and Kansas group, they also calculated and did some calculations. Yes, recent the guy in front of me has done many calculations using RDM and got some very nice result. Unfortunately, their result is somewhat disappointed to me. Maybe they disappointed also, not by non-size consistency or extensivity. So this is the finally we will explain some different problem.
What do you mean by size extensive?
Size extensive is if we double the size. Okay, there's a water molecule here, then water molecule there. The total energy should be the twice of one water molecule. This is somewhat trivial condition, but it is very difficult to satisfy by a method. This is very important. But okay. Okay, let's proceed. The matrix formulation of solving Schrödinger equation by minimizing the full density matrix is something like that. This is a Hamiltonian matrix in a huge size, which is trace is 1, and the order of size is somewhat scale like exponentially. This is not practical. So we can reduce this problem to only very small. We can reduce the problem size into very small size using 2 RDM and 1 RDM. This is a kind of convex optimization problem. We can rewrite this formulation by something like that. This is a Hamiltonian matrix, but this is only have R times R, size of 1 times R. This is a second order reduced density matrix, so this is scale like R squared. This is drastic size reduction of matrix variational formulation. But the problem here is the first and second order reduced density matrix should satisfy n representability condition. So how this convex set described by n representability condition? This is a problem. Also, calculation method is a problem, but maybe theoretical problem should be the first. So what we do was the ground state energy can be calculated only from 2 RDM and 1 RDM. Then as I described the former slide, the last slide, the first order reduced density matrix scale like R squared, R, and the size of second order reduced density matrix scale like R squared. So, this matrix should be came from antisymmetric wave function or antisymmetric density matrix. So that n representability condition is important. We know the n representability condition for 1 RDM such that the eigenvalue should lie in 0 to 1. So if we get some RDM then the eigenvalue should be 0 to 1, then this is n-representable for ensemble representable. This is not pure representable, of course. But it is known in Kuhn in 70s and Coleman in 63. So n-representability condition for 2LDM is somewhat very, very complicated. This is the open problem. For example, the 2LDM itself is R squared times matrix. And also the trace, if we take trace, is the number of particles should be n times n minus 1. So, and also P matrix, the density matrix itself is semi-definite. And Q matrix itself is Q matrix derived from density 2LDM should be semi-definite. G matrix is also derived from 2LDM should be semi-definite, and T1 and T2 prime, etc. We cannot list all of them, and may not exhaust by such kind of list. Okay.
Is it, what exactly is the open problem?
Polynomial concrete description of n representability condition on 2LDM. For example, we know
linear functions of
we know that the linear function of some the convex characterization of a convex set can be done by adding some cut. So if we identify every cut, that's done. But this is not practical. If we know such kind of condition that can be applied to plug into some different program easier, then that would be fine.
Because all the conditions, if I'm not mistaken, depend only on the depend not on the particle number, right, and not on the dimension.
Maybe.
So
No, they
Here,
do depend on the dimension.
they do depend on the dimension.
Because what the Q condition says in second quantization says, if you're, it's exactly a condition where if you take D minus n wholes, the density matrix should be positive semi-definite.
so Q includes implicitly the number of particles n and also dimension r.
But the dual problem is clear, no? The dual problem is just give any local Hamiltonian what is the ground state energy. That's equivalent.
Yes, that's equivalent, but
And
we
that's-
don't,
and that's kind of very
but
clear.
we don't know what the extreme points of the dual problem are. That's also it's just as hard.
Well, but if you have this energy function, then this is exactly what it is. It's all linear inequality. It's the trace of h times
No,
the reduced
no,
density
it's
is
a
equal to
known
the energy.
theorem that it cannot be done in terms of linear inequalities on the eigenfunction.
But if you know this energy, which is a very strange function, then this is all you need.
But you need to know all possible two-body Hamiltonians.
Yes, that's what I'm saying.
This is what Garrod
I mean,
Garrod purpose paper says. So what we need is how we can characterize a convex set is something we should know the cut, every cut corresponds to the solution to the some Hamiltonian. So that's impractical. This is so how we can make it practical is open problem, I believe. So explicit form of Q condition, something like that, and density matrix itself, and first order density matrix times Kronecker delta, and this is just a linear linear equality. There's a linear equality to gamma to Q. G condition is somewhat more simple, and here is the relationship. T2 condition is somewhat very complicated, but deriving is not so difficult. Just it is complicated. So the problems can be casted as a convex set, the described by n representability conditions. But recently, quantum computational complexity of an representability problem is QMA complete. It might not be possible to determine if the n representable in polynomial time when using quantum computer. So what we should do is something very effective and approximately representable conditions should be explained chemistry and physics. So this is a complete solution to the n representability condition is not hopeful. So we should seek such kind of approximations. The first application to atoms may be done by Garrod in 1975 and 1976. Somehow disappeared. The reason might be the lack of computer resources and poor results on nuclear systems, etc. So here is my revival. So now what we do is minimize the Hamiltonian using density matrix and n representability condition, PQG condition. Even here we want to address the computation method. The last one was theoretical part. So still not clear how to calculate, but it can be done by positive semi-definite programming. So our result was the first result. So exactly, and the first result to molecules. This is our paper appeared in 2001 and 2002. What exactly means is that we have some criterion that answer is correct within that criterion. 1970 papers are very good. They gave a very good result, but they are not sure whether the answer is near to optimum or not. Semi-definite programming is somewhat very difficult to solve for when we approach it to the optimal, because the number or the matrix becomes degenerate. So here are some results of our quite somehow old result of 2008 result for many molecular systems. We calculate carbon atoms, oxygen atoms, neon atoms, and O2 plus molecules, pH molecules, and others, and water molecules, and SiH4 molecules. So many we can apply to many systems. The state is something like defined by terms. The number of electrons are listed here: 6, 8, 10, 15, 6, 7, 8, 14, 18, 10, 15, 10. The dimension is somewhat very small, but the largest one has 28. Here is a full CI result. In this size, still full CI calculation is feasible. And here is the full CI calculation. So, given basis, the best approximation to the ground state energy. This is the best. If we employ the basis set, this is the best value. So here is a Hartree-Fock. This is a mean field theory. This is a variational theory, so we always get a higher energy than full CI result. This is CCSD plus T. This method is called coupled cluster singles double with perturbation treatment of triples. This is the golden standard in quantum chemistry when we want to calculate a very accurate result. This is a practical one. Here is a PQG T1, T2 prime. Currently, the most effective and restrictive and representability condition we know so far. Then we can comparable these results, almost the same accuracy, but this method is you may notice that this method gives a lower bound to the full CI method. This is a deviation from the full CI energy. So this is a deviation from Hartree-Fock and the full CI energy. So that's why this is a plus and this is a minus. We always have a lower bound to the exact energy. But if we compare to thesis difference T, the result seems to be very accurate, almost comparable to thesis difference T. We don't have any parameters on that. So let me explain semi-definite programming. Optimization techniques should not be done without semi-definite programming. Semi-definite programming arose from the optimization field that they optimize A0 times X such that AI dot X equals B. X equals semi-definite. I'm not sure why optimization people do so, but this is a very good approximation to max cut problem, which is known to be very hard. The semi-definite realization to max cut problem gives very good approximate value. So that's why optimization people are interested in semi-definite programming. But somehow quantum chemist I'm talking by myself. That the semi-definite programming can be applied to quantum chemistry. So here is we can regard this is a Hamiltonian, and this is a two second-order reduced density matrix subjected to something like a number of particles, number of spin operators, something like that, under semi-definite condition. So we can. This is a very abstract one, but if we think about this, we can easily translate it to variational optimization of two second-order reduced density matrix. We also define. This is somewhat similar to linear programming. Some of you may know about linear programming, and this is almost direct extension to linear programming 2 and linear programming to matrix variables. So that why we have primal dual problem. Once primal is known, dual is automatically defined. This is a dual. This problem consists dual one. So since 1995, optimization people started to solve semi-definite programming, and they are very active to developed a very good algorithm to solve this problem. This is called primal dual interior point method. This is a very well established algorithm and many good implementation like SDPA, which I use. So we solve such kind of problem, which can be casted as a 2-Valdian variational problem. We can the iteration process of these 6 steps. So first we choose some initial points and calculate shear complementary matrix and solve the linear equation, compute max step length, and update current point, and stop if is a satisfied criteria, then iterate. So we get the very good result. So what new for semi-definite programming is that very good point of semi-definite programming is we never stuck to local minima. This is a very good point of convex programming. Some people may do Hartree-Fock calculation on computers. You may get stuck into local minima. Even we do not know the result is the lowest one or not. This is a very bad point of Hartree-Fock problem, but this is a convex optimization. We always get local minima. But quantum many-body problems can be casted to exactly to semi-definite programming. So good quantum numbers, something like spin squared and n squared and alpha squared, can be conserved by linear constraint. So this is almost trivial. the number of iterations need to achieve minima is polynomial. So our method is very good. Semi-definite programming can be solved in polynomial time. This is a very good point. Unfortunately, this is not known for Hartree-Fock case. Even usually, we solve very fast, and well, there's a very good implementations, though. But even Hartree-Fock, this is the approximation method, is very hard. The very fast massively parallel implementation is available on GPU and CPU. Last year we submitted a paper, conference paper is accepted in supercomputing to 2012. But still it is very hard to optimize. Bad news is here still not so large calculations possible, and attaining very accurate solution is theoretically difficult. Therefore multiple precision we implemented multiple precision calculation. So problem in semi-definite programming is that when the solution becomes optimal, the number the condition number diverges. So very accurate solution cannot be obtained. This is a bad point of the semi-definite program. But optimization people do not need very accurate solution, but quantum chemist is. So here's an application, two-dimensional Hubbard model. Two-dimensional Hubbard model is Hubbard model. Hamiltonian Hubbard model can be described like that. And here is a hopping term. Here is a repulsion term. This is what I calculated. This is the electron, just hop. If the two electrons are the same lattice site, the electrons repulsive. It is not possible due to Pauli principle because there's two electrons on the same site and the same state. This is not possible. So minimize the Hamiltonian with respect to 2LDM. This is straightforward to apply our method using 2LDM method. We can apply chemical physical system as well. So why I calculated Hubbard model is that there are some reasons. So it is believed that two-dimensional Hubbard model is the simplest model that exhibits high TC superconductivity of copper oxide. This is very motivative and simple and theoretically important for strongly correlated system. This is the Hubbard model. So chemical system is somewhat much more easier than physical system. Hubbard model cannot be solved by Hartree-Fock. Mean field doesn't work, and CCSD coupled cluster approximation doesn't work for Hubbard model. It doesn't work. And our method can be applied straightforwardly, very easily. Just change the input file. That's fine. So large calculation of the large size of Hubbard model is challenging. Condensed matter physics people are trying to calculate 2D Hubbard model in large size, but it fails because the number of states they conserve grows exponentially. So this is a very difficult problem to. And also quantum Monte Carlo doesn't work because if the size becomes larger, the temperature that controls the accuracy of the system doesn't go to zero. We are interested in near zero temperature quantum system, not for high temperature quantum system. So the final clue, final help from full CI, this is the exact diagonalization, is also not feasible, as I explained earlier. This situation doesn't change for chemistry, from chemistry to physics. Even the largest size one is 20 lattices. It was done in Toyama in 2007. So this is very challenging problem. So finally, I should note that Brecht et al. Solved the 6x6 system, which is larger than our result. Is it published? Just accept it.
It's on the archive.
Oh, okay, on the archive.
Or what do you mean by 20 lattices? 20 lattice size?
20 lattice size is somewhat odd lattices that rotate the lattice so that fit in the 20s, which contains only 20
20 of what?
side.
Side. But it's still two-dimensional.
Yes,
lattice.
yes. Square size.
Oh, 20 times 20.
No.
20 points. in total.
20 points.
Oh,
But
4 times 5 for example.
No.
No.
But rotate the square, then fit to the interior point should contain 20 lattices. That size. Okay, so this is a tweak, strange tweak. But 24 is very difficult. Larger than 20 is very, very difficult. So it is not feasible. So here's the fourth, which we just our calculation only treat 4 times 4 lattices. Unfortunately, this is and still feasible by exact diagonalization. So, but we can compare with that. 16 electron with spin 0, the largest configuration with this lattice, and various U over T and representability conditions. This was published in 2000, this year. Okay. This is an exact diagonalization result. U over T controls the strength of electron correlations. And the intermediate part, this part is most interesting. So the weak coupling regime, almost the same result are obtained by various conditions, PQG, PQGT1, PQGT2 prime. This should be the most accurate one. So we compare the errors, very small. This is the errors, absolute errors. So unfortunately, when we got larger electron coupling constant, the errors becomes larger. But if we compare it to PQG to PQGT1, PQGT1 T2 prime gives one magnitude accurate than those results. So our conclusion is that RDA method with PQGT1 T2 prime and representability condition gave very good energies.
I want to ask a little bit about superconductivity.
Yes.
You mentioned that as a motivation.
Yes.
Couple of questions. One is, I presume if you wanted to look for the occurrence of superconductivity in your solutions, you could hope to see it rather directly in the 2RDM. Is that correct?
Yes.
Okay.
Yes.
Did you see? Well, I guess the other thing is that, from what I know, you actually would not expect it at this number of electrons. You actually you want it in the quote doped case.
Yes. So we want to calculate. Of course, we are looking for larger calculation. Say 100 times squares.
Okay, but even here, you could ask, what if you do 14 or 18
still
electrons?
not feasible.
But for superconductivity, it's well known that you can use you have the BCS state, and for the BCS state, you do know what the n representability conditions are. You know the exact form of the two-body reduced density matrix.
Well, but those are mean field states that don't preserve particle number, and these are all particle number preserving calculations, right?
No, you can do that I can do it with conserved particle number. In fact, I can even do a generalization of that. I can show you.
Okay, so what do you conclude from that? That indeed you could...
I think for the type of states that you're interested in for superconductivity, you can give sufficient conditions for n representability that would allow you to do a large body of calculations.
Okay, but do you agree that the kind of calculations that are being described here would capture superconductivity if it were present?
I agree completely.
Okay.
So what we want to know is other size and see the eigenvalues. If we find some large eigenvalues, it is likely that the superconductivity is exhibit. So summary of my talk with here. RIKEN method is possesses semi-definite type representability condition. It is a quantum chemical method which scales polynomially. It doesn't have any empirical parameters like DFT, and we do not have local minima in the energy. So calculation is very good, sophisticated. The RIKEN method doesn't depend on Hartree-Fock solutions, unlike post-Hartree-Fock method like Miller-Placer perturbation theory and coupled cluster theories and other variants of quantum chemistry. So it is very rare case that doesn't depend on Hartree-Fock solution. PQD T1, T2 prime representability condition is quite good even for high correlation system like two-dimensional Harvard model. Largest deviation was 0.03 per site. Unfortunately, recently, this is not so. We need much more, maybe more representability condition for more larger dimensional, two-dimensional Harvard model. But this is quite hopeful. For atoms and molecules, we get 101.1% of correlation energy, so this is very good. Bad news is method is size consistent or size extensive. So if we calculate larger we want to calculate larger system, maybe we needed more representability conditions. We want to do chemistry so that the error itself is not so, absolute error in the energy is not so very important, but the energy difference, why this chemical reaction occurs, is much more important. But in that case, size consistency is or extensivity is very important. But the theoretical analysis by recently done by ourselves, my group, me and my friend is not so doesn't give a positive answer. And also complete in representability condition may not scale polynomially. It is QMA hard. So still computational cost is somewhat disappointing. So this is an open program in 2RDM method. So we need more representability condition, even though but chemically and physically important ones. We need chemically and physically important ones. Maybe something is Hamiltonian dependent. We are only interested in Coulomb interaction, not a general interaction, just Coulomb interaction, which depends on the distance of two electrons. And also we need size consistence of extensive conditions. The total energy and the physical properties should scale linear with respect to system size. So I explained just before, the water molecule, one water molecule should, if we have two water molecules far apart, then the total energy should be twice of the one water molecule's energy. So this is a very important properties. And also we do not care about pure ensemble representability. For example, usually resultant RDM has AGPOA function as one of the pre-images when Hamiltonian has time reversal symmetry and system is singlet. So 90% of chemical interaction can be occurred in singlet state. In that case, almost one RDM is always have a pure pre-images, whereas 2RDM is not, for 2RDM it is not sure, but 1RDM has a pure pre-images. And also we believe that degeneracy can be removed in most cases because of applying some perturbation to the system. Okay. If we degenerate, so we can add some simple perturbation to the system, so we can break the degeneracy. And we need more faster method to semi-definite programming, or alternative method which is not use semi-definite programming. This is even though this semi-definite programming can solve semi-definite programming problem polynomial time in polynomial time and in polynomial resources, but it costs too much at this moment. And finally, importing, exporting results or discussion to quantum marginal problem. So this is what I expect from quantum marginal people. So thank you very much for your attention.
Anything? Oh, that's very bad.
I don't understand your comment about the AGP. Are you claiming that the kinds of calculations you do end up with AGP wave functions?
No. Typically, Hamiltonian is time invariant, and if we have Coulomb interactions and the kinetic part and the external potential is just nuclear, came from nucleon. In that case, the one RDM should be evenly degenerated, the singlet state. In that case, the wave function can come from AGP wave function.
The one body, but you're not using two body AGP.
Two body, not one body. One body operator part is pure, but I'm not sure for two body part.
Okay, but I guess I don't see the relevance of the AGP wave function to what you're doing.
Oh, I can show you a paper in Smith in 1966 or so.
Can I ask a couple questions?
Yes.
Just real quick, what is AGP?
Antisymmetric geminal power.
Ah, okay. Okay. The second question is, what's the main bottleneck for your calculation? Is it actually calculating these conditions during semi-definite programming?
Semi-definite programming is the most demanding part of.
But computing the conditions is not hard. Computing the conditions is T1.
Well, also, this is important, but that means you want to find some more representative conditions. This is important, but since 2004 by Brahm's paper, it doesn't have a good progress.
My last question was on the second slide or so. You said that calculating electronic energy was 98% of.
Yes.
What's the other 2%?
Okay. My wife is doing relativity theory.
Okay.
This is, and also my friends doing dynamic program. Dynamics is very important. Do you know QMMM?
Yes.
Yeah, MM part is dynamic, somewhat. It is not purely quantum dynamics, but classically dynamic.
So, sort of related to what is bottleneck? Can you? So, if I understood correctly, the conditions that you use, obviously not the full set of conditions, but the ones you used that did pretty well, involved. Is it right that involves looking at whether certain n cubed by n cubed matrices are PSD? Is that the right way to think about them? And the more general question is, what is the size? Asymptotically, how does the size of your SDP grow with n, and how does the runtime grow with n?
This is accurate. Maybe. We are very naive. We are using very naive implementation. So here is the computational cost and complexity. The number of iteration itself is scale like R logarithm epsilon over -1.
What is R?
R is the number of basis set. A number of bases in the basis set.
And what's the dimension of the? So R to the 12. That means that's because the matrices are R cubed by R cubed.
If we use P and Q matrix scale like R squared. R squared, R squared. If we use PQG, T1 condition, T1 or T2 condition, it becomes R to the 6 and R to the 6. Sorry, R to the 3, R to the 3, cube, R to the cube, so R to 3, R to 3. So, sorry.
And have you ever looked at solving these with something like a method of alternating projections, or is it not clear how to, is it not clear how that would work?
Projection method.
Yeah. Well, maybe we should talk later about what exactly
Okay.
means.
Right.
So does translation variance help, or can we exploit that in some sense to come up with faster objects?
Sorry.
If you would have a system that is translation invariant, like the Hubbard model of torus, how would you exploit this?
So if we have some good quantum number or symmetry, we can reduce the number of variables. That's all. But if very easy symmetries or something like that, it just reduces the number of variables. But if we know the very good symmetries, I'm very sure that it increases the energy a bit more to push up the energy to get more accurate results.
But it would be much simpler because you have less variables. So.
Of course, it's done by introducing symmetries is done by very standard, so that they can solve larger systems.
But what is the scaling then?
Scale doesn't change, just the same. But you reduce the prefactor drastically if we introduce the symmetries. Well, I'm not sure that some symmetries are very good enough to reduce the scaling. Maybe it happens.
Are there any more questions? Then I suggest we thank the speaker again.